Let's move on now and talk about infinite geometric series. So we had this example in the finite geometric series where we started with 5 and we kept multiplying by 2/3. Right, we kept doing this. Let's multiply the top by 2 and the bottom by 3, but now I want to let it go on forever. But just a reminder, so what we did here is we multiplied by 2/3 each time to go from one term to the next, right? And you're supposed to keep doing this forever. So in the previous video, we stopped, I think, at 80/81. But I want to keep going forever with this. And I want to try to think about, does this sum make sense? It's an infinite sum. Does it make sense, right? And let me just rewrite this. Let's just write it a little more explicitly. 5 plus 5 times 2/3 plus 5 times 2/3 quantity squared plus 5 times 2/3 quantity cubed. And I guess one more, 5 times 2/3 quantity to the 4th, and so on. So remember, this is called a geometric series when you multiply by the same multiplying factor. So r equals 2/3 here. It's the sort of the multiplying factor. That's what makes a series called geometric, is when that's how we move from one term to the next. And so we could write this way. We could also write it in summation notation if we like. It's the sum from I equals 0 to infinity, 5 times 2/3 to the I. Notice that we started I equals 0 because it's there's kind of like a 2/3 to the 0 power right here. Oh my God, that doesn't look like a 0. Still doesn't look like a 0, but hopefully you realize that's a 2/3 to the 0 power. So we would start counting from 0. All right, and the thing is, we would like to know if this has a sum, if it converges or diverges, right? We use this language for infinite series. It's like we use for improper integrals. Does it have a finite value? Does it go on? Does it not? Does it blow up and get larger and larger? We're adding infinite numbers. We're adding an infinite series of numbers together. Seems like it could possibly just blow up to infinity. And as always, what we do is we analyze the partial sums, right? So we want to know, does this converge or diverge? Let me just write this. So question is, does this converge or diverge? And so what we do is we look at the partial sums. So we call Sn the sum from I equals 0 to n, 5 times 2/3 to the I, but we can also write this as 5 plus 5 times 2/3. Actually, put on the next line. So if I want to write this out, 5 plus 5 times 2/3 plus 5 times 2/3 squared plus ... plus the second to last term would be n minus first power. So that's the term before the nth power. So it would look like that, right? And remember, for the subscript n right there, okay. So remember that the, oh my God, there's these artifacts on the screen. I don't know if they're actually there. Where did this come from? What is happening? It's frustrating. Sorry, there were some artifacts on the screen. I don't know if you could see it in the video, but I just want to keep going. Okay, so so the idea that we saw here was, what if we, the kind of the neat concept here is to use the structure. There's a structure inside this sum that we're multiplying by 2/3 to get from one term to the next. So let's multiply the whole thing by 2/3. So we look at 2/3 times this partial sum. And we're going to multiply each term by 2/3. So I'm just going to go ahead and write that down here. 5 times 2/3 is the first term, right? We're multiplying by the 5 by 2/3, and then we multiply the 5 times 2/3 by another 2/3. So we get 5 times 2/3 squared. And then we multiply the 5 times 2/3 squared by another 2/3. And there's a term here, but I'm going to kind of just let that fade into the dot, dot, dot. There's a term just before the 5 times 2/3 to the n minus 1. That'll be 5 times 2/3 to the n minus 2. And so when we multiply that by 2/3, we get our 5 times 2/3 to the n minus 1, 5 times 2/3 to the n. And there's this extra term. So I can make this fit. 5 times 2/3 to the n plus 1. Right? So we multiplied that term by 2/3, and we got the nth power. We multiply the term with an nth power by 2/3, we get the n plus first power. Okay. And then the kind of cool idea is that now we see that, you know, all these terms are sort of in common, right? Like the terms on the first line and the terms on the second line are in common. So if we subtract, we get all this cancellation. And we get s sub n minus 2/3 s sub n. And then we get just the first term minus the last term, the 5 times 2/3 to the n plus 1. And that's all that's sort of left, right? Everything cancels. The left-hand side becomes 1/3. We've taken one thing and we've subtracted 2/3 of itself, so we get 1/3 of itself. And we get 5 times, I'm going to factor out the 5. In some ways, what I'm doing here is I'm just rederiving the finite geometric series formula, right? This should look exactly like the finite geometric series formula. So s sub n is 3 times, I multiply both sides by 3, so the 5 becomes a 15. And then we get this expression, right? But now we want to think about the infinite series. And the whole point of the infinite series is we look at the limit of the partial sums as n goes to infinity. So S is what I called the whole thing, right? This was S. Or down here, or down here. Okay, that's S. I call that S. S is the limit as n goes to infinity of S sub n, of the nth partial sum. So S is the limit n goes to infinity of S sub n, which is the limit as n goes to infinity of 15 times 1 minus 2/3 to the n plus 1. And now what happens as n gets large? Well, look, if we take 2/3 and we multiply itself, we get 4/9. We multiply itself again, we get 8/27. The numbers get smaller, right? When we take a number between 0 and 1 to you know, a larger and larger power, then that gets smaller and smaller. And so this goes to 0 as n goes to infinity. And so in fact, we just get 15 times 1 minus 0, which is 15. And that's our answer. That's the sum of this infinite series. it's, if we take, if we go all the way back to the top here and look at this thing, this right here, 5 plus 10 thirds plus 29 plus 40 over 27 plus 80 over 81 plus dot, 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 and so on, keep the pattern going, then sort of miraculously, it actually adds up to a finite number, and that number is 15. Okay, so that's kind of nice. Let me just do one more example before I give you the general formula, because I think it's going to be, or maybe one or two more examples because it's going to be instructive. Let's do something like this. Let's actually start with 5 again, but instead of multiplying by 2/3, let's multiply by 1/3. I mean, sorry, by 4/3. So let's consider the sum 5 plus 5 times 4/3 plus 5 times 4/3 squared. I could write this all out, 4/3 cubed, and so on. Just as before, we did have this, we had this finite geometric series from this. So rather than going through the whole trick here, we're multiplying by, rather than going through this part, this argument here, just going to remind ourselves that we actually kind of derived the general formula for this. So this, remember, we called this, this first term we called A, and the multiplying factor we called R. So this actually looks like that. And we said that we had the finite geometric series formula that we derived before, which said that if we stop at n, so Sn, it's A times 1 minus R to the n plus 1 over 1 minus R. That was the formula we derived. And you could check that, by the way, against the previous example to make sure that it agrees with the formula we got right here. And if we plug this in here, if we plug in A equals 5 and R equals 4/3, we get, so here, S sub n, the nth partial sum, is 5 times 1 minus 4/3 to the n plus 1 over 1 minus 4/3. And you can certainly simplify this part if you want. But the big deal, the big question is what about this part right here as n goes to infinity, right? Now we're multiplying something that's bigger than 1. 4/3 is bigger than 1. And so that means S, the sum itself, is the limit. We always take the limit of the partial sums. That's the limit as n goes to infinity. Okay, I've got this 5 over 1 minus 4/3. Simplify if you want, but the real thing that happened, the real part that's going to be affected by n going to infinity is this term right here. And this is going to blow up, right? This is going to get bigger and bigger as n goes to infinity. So this actually goes to infinity. Goes to infinity as n goes to infinity. So now we've got a problem. We're actually, this is blowing up. This is a number. You could even check to be sure, like the denominator here is a negative number. This is also a negative number because 4/3 is bigger than 1 and 4/3 powers is bigger than 1. So that's okay. They negative or negative cancel, you get positive. So this actually does go to positive infinity, and it diverges. Okay. Yeah, and it's really because, the multiplying factor R was bigger than 1. And you can sort of see that if you look back in the original sum, right? Like these numbers are getting bigger. You're adding bigger and bigger numbers each time. It's going to keep going. And you're just going to be adding bigger and bigger numbers. So you really do expect this to diverge. But this is kind of the argument that it actually is happening, right? Okay. And so if we wanted to generalize this, actually, I'm sorry, let me give you one more quick example. It turns out R can be negative. We didn't really think about what happens when R is negative. So what if we did something like, you know, 3 plus 3 times negative a half plus 3 times negative a half squared plus 3 times negative a half cubed, and so on. So this starts to look a little weird because if you wrote out what these are equal to, right, it's 3 minus 3 halves plus 3/4, because when you square a negative, you get a positive, minus 3/8 plus 3/16 minus 3/32, and this is the pattern you get. But the exact same argument works with, it doesn't really matter what R is, right? I mean, here A is 3 and R is negative a half. And so if we use the geometric series, the finite geometric series formula, we see that S sub n is A, just 3 times 1 minus R to the n plus 1 over 1 minus R. And so it's a little funky because, you know, in this example, you're subtracting and then adding and then subtracting. We're going to see this later. This is actually called an alternating series, where you alternate adding and subtracting numbers. And so this actually simplifies. I mean, it's sort of interesting, but the numbers are getting smaller. So you're adding back and forth. You're sort of moving left around the number line by adding, but the numbers are getting smaller. So it's kind of coming to a stop. I mean, this will come up later and I'll draw a picture, but the bottom, so you get 3, the bottom 1 minus negative a half is actually over 3 halves. And you get times 1 minus negative a half to the n plus 1. And now as n goes to infinity, again, even though it's a negative number, it's still, in absolute value, it's smaller than 1. So when you take powers of negative 1/2, they still go to 0. Goes to 0 as n goes to infinity. And so this term will go away. And so you really just, S will be the limit, this whole sum, infinite sum will be the limit as n goes to infinity of S sub n. And if you think about what you did there, you get 3 over 3 halves, which is actually 2, times 1 minus, and then this term goes to 0, right? And so you just get 2. And that's the actual answer. So you do 3 minus 3 halves plus 3/4. It's sort of plausible if you think about the first 3 minus 3 halves gets you between 1 and 2, plus 3/4 makes you a little bigger than 2, minus 3/8 is a little less than 2, and it sort of hones in on 2. And so this is a convergent geometric series. Okay. And now just to finish this off, the you can kind of get a formula. You sort of see what's happening when this converges, right? Because in general, if we just write our sort of generic infinite geometric series going on forever, so we can think of it as a sum from 0 to infinity of a r to the n, or I guess I was using I, not to confuse with the nth partial sum, then S, if we just take the limit of the partial sums, we have this partial sum formula. So that's the limit as n goes to infinity of a times 1 minus r to the n plus 1 over 1 minus r. And it's all about what's going on in this part right here, right? Everything else doesn't, that's the only place where you have an n. So what happens to that as n goes to infinity? And well, we've sort of started to see now, right? If r is smaller than 1 in size, it could be negative, but it's got to be smaller than 1 in size. So let me write this as a general statement, right? The limit as n goes to infinity of r to the n, just takes r to the n plus 1, doesn't really matter. They're both going to go to infinity. If r is between -1 and 1, then that's going to go to 0. And by the way, I could rewrite that as the absolute value of r is less than 1. And if the absolute value of r is greater than 1, then it's going to blow up and get bigger and bigger. So this is an important sort of side over here, because that's going to show us what's going to happen if r is, so this is going, so basically the sum I equals 0 to infinity of a r to the I is going to equal, it's going to be this formula, right? It's basically, again, this term, either it's going to go to 0 or it's going to blow up. And so we're going to get a times 1 minus 0 over 1 minus r if the absolute value of r is less than 1. And it's going to blow up if the absolute value of r is greater than 1. And so in fact, this is sort of, this part of it's sort of nice. This actually simplifies to just a over 1 minus r. And this is kind of a famous formula if you may have heard of, if you've ever looked at this stuff before, or anybody who studied this will remember this, or if they can conjure from their memory, will remember this formula that, so if the absolute value of r is less than 1, then the infinite series has this nice formula, a over 1 minus r. And this is the infinite geometric series formula. This is a convergent. So the infinite, yeah, this is like the infinite geometric series formula. But it only works if the number r is less than 1. Right, and then if r, well, so if absolute value of r is greater than 1, then we know it's going to diverge. But also it turns out that if r is plus 1 or minus 1, I mean, we didn't really think about those cases, but if r is 1, right, then the sum I equals 0 to infinity a r to the I is kind of silly. It's just r is 1, so you really just get a over and over again. And that's going to clearly diverge. You're just adding the same number, I guess if a is not 0, but if a is 0, what have we been doing here? So that diverges. If r equals -1, that's kind of an interesting case that's worth thinking about a little bit. You base it, and let's forget about, let's just pretend a is 1 so we don't have to think about it. So you get the sum of -1 to the I. So you actually get 1 plus -1 plus 1 plus -1 plus 1, because you take powers of -1, right? And it just bounces back and forth between 1 and -1. And here's the thing that's kind of interesting. If you think about the partial sums, right? You get 1, but then if you add 1 plus -1, you get 0. And then if you add another 1, you get 1. And then you add another -1, you get 0. And so the partial sums actually bounce back and forth. And so they kind of do that forever. And this is actually, so the limit doesn't exist because it's bouncing back and forth. So this actually diverges also. Even though it's finite, it doesn't go off to infinity or anything, but it's called sort of oscillatory divergence, where it just bounces back and forth. So in fact, if r equals 1 or -1, this series diverges. So we can actually say in general, if the absolute value of r is greater than or equal to 1, then the sum, the infinite geometric series, diverges. And that covers all the cases, right? Because the absolute value of r is either less than 1 or greater than or equal to 1. And so these are the two cases, I guess, if I want to include the r less than 1 there. And that's it. That's infinite geometric series. That's sort of the general. By the way, it's also worth checking this. First off, it's good to get this in your head, this formula right here, a over 1 minus r, and you can check it against the examples above to see that it actually gives you the right answers. And you'll see that it does actually. You'll get 15 out of this example. You'll get 2 out of this example. And yeah, that's it. All right.